We have introduced some techniques to estimate time series models, but so far we have dealt with single questions only. It is not uncommon for us to have several equations to be estimated simultaneously. That's when we need those vector models, and that's the focus of this particular module. So we're going to introduce vector error correction model and vector autoregressive models. Those are extensions of the error correction model and autoregressive model we introduced for the univariate cases. We will introduce the techniques and also demonstrate how to do so in Stata. First of all, we need to introduce some jargons. In the first equation on the slide, the dependent variable is yt. We usually say that we normalize on y. And in the second equation, we use xt as the dependent variable, but yt as the independent variable. So we swap them in this equation. That is still valid, but the focus of the study has changed. It's on xt. So we will say this model is normalized on x. An univariate analysis examines a single data series. So for example, the AR1 process we investigated before, that's a typical univariate analysis example. Bivariate analysis examines a pair of series. So either one of those two equations on the slide is a bivariate analysis example. Vector analysis, on the other hand, examines a number of series. It could be one, it could be two, it could be more. In other words, vector analysis is a generalization of the univariate and bivariate analysis. We are extending our discussions in the last two lectures to a more general case. So let's look at a vector autoregression model. We have yt, xt. We also have lag terms of both variables in the equations. Because the maximum lag is of order 1, you may notice that we have only t-1 terms in both equations. We have a VAR1 model. If both y and x are I1 and not integrated, we need to estimate the two equations simultaneously as on the slide, that's on the bottom. So we have the first difference of both yt and xt and their lag terms in these equations, because both of them are not I null and they are not integrated. The only way that we can satisfy the assumption of linear regression is to take the first difference of both variables and use the first difference, which is stationary, in this VAR model. However, if both x and y are I1, but they are co-integrated, we can estimate a vector error correction model, VEC model. So for example, if y and x has a long-term relationship, as shown here, so yt equals beta null plus beta 1 xt plus et, that's the long-term relationship. Both yt and xt are not stationary. The vector error correction model can be specified as follows. So we use the first difference of yt and xt as the dependent variables because both of them are stationary. We then use the error from this long-term equilibrium or long-term relationship equation as a variable in these two equations. So this part as a whole is stationary because it's co-integrated. Then we have both models satisfied the assumption of linear regression. On top of that, the coefficient of those error correction terms have economic meanings. So alpha 11 and alpha 21 are known as error correction coefficients. Alpha 11 should be negative, and the rest of the EC coefficients should be positive. So you may notice that the expression of this long-term relationship or the error correction term implicitly use yt minus 1 as the dependent variable. So that's the difference between y and yt and yt hat if you have beta b1, b0, b1 estimated. So when you have xt or delta xt as the dependent variable, the error correction term actually is swapped. So this is why the sign of those alphas should be opposite between the first one and the rest of the equation. You may have more than one x. So this is just a simple example, simplified example, just to show the structure. So if you have x1 t minus 1, x2 t minus 1, x3 t minus 1, you will have one error correction model corresponding to each x. So you will have more than one alpha corresponding to those x's. The first one should be negative. This is the way to adjust. This is because for any positive deviation from the long run equilibrium, you need a negative adjustment so that in the long run, gradually it can go back to its equilibrium level or correct any deviation. Same thing is true for all other x's. The correction must be to the opposite direction of the deviation. Otherwise, it's not a correction. So this is the quick way to check whether your error correction model or VEC models are sensible, because all else being equal, the first alpha should be negative and the rest should be positive. Otherwise, you will have a great difficulty to interpret the result. They should be either 0, no effect, or the first one is negative, the rest are positive. So that's the interpretation of those coefficients. Now, let's have a look at the procedures to estimate a vector error correction model. Typically, there are two steps. The first step is to estimate the co-integration relationship, and then to generate the lagged residuals to be included in the second step. So the second step, we're going to estimate two equations together. And you may notice that we use ET minus 1 hat in both equations. Those are the error correction terms. That's from the first step. Now let's use one example to illustrate how to estimate the model. We have a quarterly real GDP of a small economy, relatively speaking, Australia, and a large economy, that's the United States. And if we plot the line chart, the time series chart of both series on this diagram, we may notice that both of them are moving together quite closely. So the first step is to check whether we have a co-integration between the two variables. We omit the intercept term because it doesn't have any economic meaning. This is because if you have intercept term in this equation, you're basically assuming that there is a constant gap between the two countries' quarterly GDP in every single quarter. I just don't think we have any economic support for such assumption. Basically, that's quarterly change. If you accumulate, that's going to be a very big trend over the long run. So there is no constant, and we perform a unit root test on this equation. So the test statistics is minus 2.889, and the critical value is minus 2.76 from the table that I gave to you in the last lecture. So we reject the null hypothesis. The two series are co-integrated. In this type of test, the null hypothesis is unit root, or the series is not stationary. We then use the lagged residual series from the first step to estimate this VEC model as shown on this slide. So we have the coefficient estimate for the error correction terms and the coefficient estimate for the lag terms for both the dependent and independent variables. You may notice that the first error correction term is negative and significant, which is consistent with our expectation. The interpretation of this coefficient is Australia's quarterly GDP will adjust about 10% of the deviation of h from its co-integrated value 0.985 ut minus 1. So that is actually from the model that we estimate over here. So this is a long-term relationship. In the long run, Australia's quarterly GDP is about 98.5% of the size of a United States one. But in the short run, from time to time, there will be some deviation from this long-term relationship. And the system, or Australia's GDP or economic system, economy will adjust by about 12.8% each quarter in order to get back to that long-term equilibrium. However, the error correction coefficient in the second equation is not significant. So this minus 1.17 is well far away from the rejection region. So we do not reject the null hypothesis that its coefficient is 0. So it looks like it's negative, but it's just random deviation from 0. This coefficient should either be 0 or positive. That's the second equation, by the way. And our interpretation is the small economy is likely to react to economic conditions in the large economy, but not vice versa, which means Australia's one will follow suit, will make adjustment, is lagged, but United States one will just press ahead. It's kind of the leader.